Hey guys, this is Aniket here. This is my presentation for my project in the EEL 6825 pattern recognition course. My project is face recognition using principal component analysis. Going forward, the facial recognition is an active area of research, and although it may be trivial to humans, it is very tough to imitate artificially. Some of the latest face recognition algorithms make use of machine learning and perform quite well. However, the training amount and processing time is massive. Given here is an illustration of a face recognition system. So as you can see, a face recognition system takes a face image as an input, which is used by the system for classification. Initially, pre-processing is done on this image, which involves removing noise and other unwanted elements from the image. The image is then passed on to the classifier, which decides to which subject in the database the input image belongs to. And finally, the classifier makes use of the trained images to predict any image that is given to it, by indicating whether the subject in the input image is present in the database or not. So my project will make use of the OpenCV face recognition software and the inbuilt algorithms. OpenCV makes use of three major algorithms: the eigenface algorithm, Fisher face algorithm, and local pattern binary histograms. The implementation will be done using Python in a Windows-based environment. And I've also extended the project to make use of the webcam for a real-time face recognition system. So initially, as can be seen in the report, the literature review consists of understanding the three approaches that are used by the OpenCV modules. The first approach is eigenface. The first problem that we face with image representation that we are given is this high dimensionality. Two-dimensional grayscale images span a large dimensional vector space. So an image with say 100 by 100 pixels can easily lie in a 10,000 dimensional image space. The question is, are all dimensions equally useful for us? We can only make a decision if there's any variance in data. So what we are looking for are the components that account for most of the information. The principal component analysis approach, which was independently proposed by Carl Pearson and Harold Hotelling, turns a set of possibly correlated variables into a smaller set of uncorrelated variables. The idea is that a high-dimensional dataset is often described by correlated variables, and therefore only a few meaningful dimensions account for most of the information. The PCA method, the principal component analysis method that I've used in my project, finds the directions with the greatest variance in the data, called principal components. The other algorithm that OpenCV makes use of is the Fisher face technique. The Fisher face technique is more advanced than eigenface in the sense that it makes use of linear discriminant analysis. Although the principal component analysis, which is the core of eigenface method, finds a linear combination of features that maximizes the total variance in data, it doesn't consider any classes, and so a lot of discriminative information may be lost when throwing components away. Imagine a situation where the variance in your data is generated by an external source, say light. The components identified by a PCA do not necessarily contain any discriminative information at all, so the projected samples are smeared together and a classification becomes impossible. The linear discriminant analysis used by Fisher face performs a class-specific dimensionality reduction and was invented by the great statistician Sir R. A. Fisher. He successfully used it for classifying flowers in his 1936 paper, The Use of Multiple Measurements in Taxonomic Problems. In order to find the combination of features that separates best between classes, the linear discriminant analysis maximizes the ratio of between classes to within classes scatter instead of maximizing the overall scatter. The idea is simple. Same classes should cluster tightly together while different classes are as far away as possible from each other in the lower dimensional representation. Next, the OpenCV technique also contains another function called local binary patterns histogram that forms the third and the last recognizer. Although eigenface and Fisher face take a somewhat holistic approach to face recognition, in which you treat your data as a vector, sometimes in a high-dimensional image space, we all know high dimensionality is bad. So a lower dimensional subspace is identified where probably useful information is preserved. The eigenfaces approach maximizes the total scatter, which can lead to problems if the variance is generated by an external source like light, because components with a maximum variance over all classes aren't necessarily useful for classification. So to preserve some discriminative information, we applied a linear discriminative analysis and optimized as described in the Fisher face method. The Fisher face method worked great, at least for some constraint scenario. Sorry. Now, real life isn't perfect. You simply can't guarantee perfect light settings in your images or 10 different images of a person. So what if there's only one image for each person? Our covariance estimates for the subspace may be horribly wrong. So will the recognition. Remember, the eigenface method had a 96% recognition rate on the AT&T face database. How many images do we actually need to get such useful estimates? In order to get good recognition rates, you need at least 8 plus or minus 1 images for each person, and the Fisher-Face method doesn't really help you. So some research concentrated on extracting local features from images. The idea is not to look at the whole image as a high-dimensional vector, but describe only local features of an object. The features you extract this way will have a low dimensionality implicitly. You'll soon observe that the images that we are given doesn't only suffer from illumination variations, but other problems like scale, translation, or rotation immediately come into picture. The local binary patterns methodology has its root in 2D texture analysis. The basic idea is to summarize the local structure in an image by comparing each pixel with its neighborhood pixel. If the intensity of the center pixel is greater or equal to its neighbor, then denote it with 1 and 0 if not. So you end up with binary numbers for image representations. The implementation, as I said earlier, is again done using the Python language and the OpenCV library. So as I discussed, the principal component analysis technique is one of the most favored strategies for feature selection and dimension reduction. It was first done by Turk and Pentland, and it defines a feature space that reduces dimensionality of the initial data space. This reduced space is then used for recognition. It was a good initial method, but it had many flaws, like the poor discriminating power among the category and enormous computation that is required by this method. This limitation was overcome by linear discriminant analysis, which is used in Fisher faces, which uses PCA to cut back dimensions before applying LDA. This is done because LDA faces the small sample size problem. The method that we use initially is called eigenfaces. It is an information theory approach which codes and then decodes face images to gain recognition. And it makes use of principal component analysis to find the most important bits. The next method that we use is Fisher faces, which follows the same approach as eigenfaces, but instead of PCA makes use of the linear discriminant analysis technique that we described previously. It better handles interpersonal variability within images such as lighting, as you can see in the picture beside. Local binary patterns histograms describes local features of an object, and it does this by comparing each pixel to its neighbors. The histogram of image contains information about the destruction of local micropatterns. So the basic idea is that the problem that we faced with image representation was its high dimensionality. For example, a 256 by 256 image can easily become a 65,536 vector of dimension or a single point in this dimensional space. Now consider an image with an n square vector of dimension, so the values can get really high really quickly. But as you know, the images of faces will not differ too much. So this allows us to use a much smaller dimensional subspace to classify them. PCA analysis finds the vectors that best define the distribution of images. These vectors are n square long and describe an n by n image. They make use of a linear combination of the original face images. These vectors are called eigenfaces. They are the eigenvectors of the covariance matrix, and they resemble faces, as you can see in this diagram. So the method that we used was acquire the initial training set of face images and then use it to calculate the eigenfaces. Keep only m eigenfaces that correspond to the highest eigenvalues, and these images will now be used to define the face space. We then calculate the corresponding distribution in an m-dimensional weight space for each known individual. If any new image is passed, we calculate the weights for this new image by projecting the input image into each of the eigenfaces. We first determine if the face is known within some tolerance, that is, it is within some tolerance to the face space. If it is within the face space, then classify weights as known or unknown. We then update the eigenfaces and the weights, and if the same face repeats, then the face is used as an input into known faces. The input image can have four possibilities. Either it is near the face space and near the face class, in which case it is the known face. If it is near the face space but not near the face class, then it is a face but it is an unknown face. If it is not near the face space but near the face class, it is not a face but may look like one, thus it will count as false positive in our implementation. And if it is not near face space and not near face class, then the algorithm does not consider it as a face and thus removes it completely. The beauty about OpenCV is that a lot of this process is automated. What we need is the training images, and we need to specify the type of training and the number of eigenface values to use. We also need to specify the threshold that the algorithm uses to classify the images into known and unknown, and the input images that will be supplied to our algorithm.